Yeah, thanks very much. My name is Akbik. I'm a research associate at the Berlin Institute of Technology. For the past 5 months, I've been working at IBM Research in Olmeden, working on System T, which is their information extraction system. However, today I can't talk about this research, but I'll talk about some earlier stuff that I was doing on interactive, open, and exploratory information extraction. So the starting situation, I think we all know, is that out there's an abundance of unstructured data, mostly in the form of natural language text. And hidden in this text is information that we might find interesting, especially our customers might find interesting. So the task of information extraction is to make this, to sift through all this text, extract interesting bits and pieces of information, and extract them into a structured representation. So for example, we might have a customer who's interested in monitoring the business activities of companies. So you might be interested in knowing which company acquired which other company, for how much money, so on and so forth. And the task of information extraction basically is to gather this information from a lot of text. And the nice thing is that if we have a good system, we could potentially gather this information from large parts of the web. So this would be a good information base. If we want to build an information extraction system, we basically have two general lines of approaches. The first is a rule-based approach. The manual work here that you have to do is specify patterns, how a specific type of information is expressed in text, manually, and run these patterns on text. So here we have an example of a regular expression. That's a very simple pattern. This is a capitalized word, followed by the word bought, followed by another capitalized word. So this would be a very simple pattern for the acquisition relation, right? And so you run this regular expression on a bunch of text, and all the segments of text that match this pattern, you would extract as instances of the relation that you're looking for. Now, of course, patterns can be more complicated than that. They could incorporate a larger feature set, for example, syntactic features as well. And writing these patterns is generally not considered very easy. For this research, because of this reason, research has focused a lot also on supervised machine learning-based approaches. So here, the manual work that you have to do is you go through a bunch of text, you annotate the relation that you want into this text, then you have your annotated data, you train a classifier over this data, run that classifier on text, and extract your relation instances, hopefully. So in both cases, what you have to do is you have to be very specific about the type of information that you're looking for. This is, in a way, a limitation if you want to apply it to a practical use case. So especially for the machine learning-based approach, you have to be very specific. You have to define very specifically what kind of relation you're looking for before you start annotating a bunch of data, right? And this is problematic because in practical applications, your customer will often present you very vague information needs, vague and changing information needs. So this is a real one, actually. I work in a European project with a bunch of libraries, and they want me to mine information on preservation risks of the web. And so basically our task is to sit down with them, with our customers or with our use case partners, and basically define clear-cut extraction tasks so that we can build our extractors. And in a way, this is made even more complicated by the fact that we don't exactly know what kind of information we can find on the web. So very often we have large document collections of unknown content, and so basically we have to reconcile those two. The worst thing that could happen to us is that we sit down with our customer, we define an extraction task, we label a bunch of data, build the extractor, run it on the web text, and then find out that this kind of information isn't actually contained in there, or at least not much of it. And speed is also critical here. So we want to be able to answer the customer need as quickly as possible. So when the customer, they often have changing ideas as well. So every week they might have a new idea. And you want to be able to build your extractors as quickly as possible and say, yes, we can do this. No, we can't. So for this reason, we have looked into the notion of exploration. Basically, what we mean by that is that we want to make the task of building rule-based extractors so easy that you can basically fire rule-based extraction queries in an exploratory fashion against a large document collection and see what comes back. And we want to make that really easy, see what comes back. Basically, you look at what comes back, you refine your query, you fire another one, and basically work interactively with the data. So basically, the idea is more or less inspired from how we interoperate with Google. With information retrieval, very often we might start looking for something on the web, and we don't exactly know what we're looking for. So we go into this thing with a vague information need. We do a bunch of queries, we see what comes back, we refine the queries, and at the end, we know what we're looking for, and we have found the documents that we're looking for. And we want to have a similar ease of use for information extraction. So basically, our goal is to make information extraction so easy that you basically can just fire exploratory queries against a large corpus. So the goals are, we want to make rule-based information extraction very easy and very fast. And we want to make it so easy and so fast that you can use it for user-driven exploration of a large corpus of data. Which brings me to the overview. So in this talk, I'd like to talk about our notion of exploratory relation extraction. I would like to talk about the linguist extraction that we use to write these rules, and present two workflows and two tools, actually. I'll be showing some videos as well, of how we enable this exploratory working with the data. Then I'd like to talk about a different project where we use open information extraction technologies to mine world knowledge, commonsense knowledge from very large amounts of text data, and talk a bit about how we represent this, and maybe discuss this, how such data might be useful for you. And then I conclude the talk. But yeah, first, exploratory relation extraction. So basically, the linguistic abstraction that we use are lexico-syntactic patterns defined over dependency trees, specifically subtrees and dependency trees. We have found that this deep syntactic information is very powerful. So if you look at this sentence, YouTube, a web platform for video content, was acquired by Google. There's a long-range dependency here between YouTube and acquired. So YouTube is the passive subject of the verb acquired. And even though there's a bunch of stuff in between, we still know that the overall syntactic structure is in such a way that YouTube is the subject, right? And so this is actually very helpful. So what this allows us is to define information extraction patterns as subtrees. For example, like this one, x acquired by y. So x and y would be the placeholders for the named entities. And we require x to be the passive subject of the verb acquired, and y to be the prepositional object of the verb acquired. And the nice thing about this is that this pattern is kind of compact, and I think kind of readable. But at the same time, it matches a bunch of different sentences. So if we have a sentence like this one, PowerSet was recently acquired by Microsoft, we do a dependency parse, and we find this exact subtree in this sentence. Even though there's some words in between, there's a recently in between, it doesn't matter, because the overall syntactic structure remains the same. And even if there's a lot more stuff in between, like in the sentence in the previous slide, YouTube, comma, a web platform, blah, 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 comma, was acquired by Google. Even here, the overall syntactic structure remains the same. So the same pattern matches all these different sentences. And so if we fire this pattern against these two sentences, we get two relation instances, namely PowerSet Microsoft and YouTube Google. So the pros, or the good things about these patterns, is that they are very succinct, they're very compact, and at the same time very powerful, because they allow us to get a bunch of linguistic phenomena. They are easy to read, or at least that's what we believe, especially if you know some NLP, if you know how to read these trees. But this also leads me directly to the disadvantages. So the disadvantage is that you do have to know some NLP, and it's actually not so easy to write these patterns, especially for people who don't have a background in linguistics. Type dependencies, even part of speech tags, are very confusing to most people. And this is a problem because we believe that these patterns are very powerful, and we would like to give this power to as many users as possible without educating them about linguistics first. Yeah, and for this reason, we designed a tool and a workflow that we presented last year at ACL called PropMiner. And the basic design principles are that we have an example-driven workflow. So what we want is for users not to write these subtrees, but actually to point to one example. I want this pattern just as it is used in this example sentence. So basically provide an example sentence for the subtree that you want, annotate it a bit, have an automatically generated rule, and modify that rule. At the same time, we want to have high interactivity. So if you tinker around with this rule a bit, if you modify it, you always see exactly what this rule gives back to you over a large document collection. So the workflow basically consists of 4 steps, and I'll show a video of the tool in action in a bit. So basically, if you want to design a pattern, you basically invent a sentence. You say, I want this pattern just like it is used in this sentence. You annotate the important bits of information in this example sentence, have the tool generate an overspecified rule for you, and you modify this rule and query the corpus. Now, let's go through an example of this. So let's say we are looking, as a very common example, is the born-in relationship between a person and their birthplace. And so basically, if we're looking for this relation, the first step is to basically just invent a sentence. It doesn't even have to be true. And the sentence might be, Einstein was born in Germany. So we enter this into the tool. So that's here on the left-hand side in the top. We enter the sentence into the tool. We annotate the entities, Einstein in Germany, and we also annotate the words that express the relation, that's born and in. The tool then generates a rule, an overspecified rule, which you see on the right-hand side here. So this is not something that the human actually does. The tool generates the rule. It consists of a few clauses, basically the number of attributes that you want to project. Then the from clause is the path expression that basically defines a subtree. It's not so readable, but it's basically the same subtree for these 4 words as they are used in the sentence. And the where clause, that's the interesting one, is where the user can tinker around a bit, are basically conditions on the part of speech tags and the lexical values of the nodes in the subtree. So basically, if you look at where subject part of speech is NNP, means that the node that is the subject, that is designated subject in the subtree, has to have the part of speech tag NNP, which indicates a proper noun. And the text of this node has to be Einstein. So this is a very overspecified rule, and this rule will probably not find anything in the corpus. But what you can do as a user now is remove conditions. So you might remove the condition, the subject text does not have to be Einstein. So you want the exact same syntactic structure, the shallow syntactic structure, the deep syntactic structure. You want the same lexical values for the predicate, and the object still has to be Germany, but the subject can be any text, right? And by removing this condition, now this rule actually matches a bunch of sentences in the text, in the corpus. And you can basically look through all these sentences. You see the subject, predicate, object relation triples, and you can see how this rule matches the text. But this is not what we actually wanted. We wanted a born-in relationship for anything, right? So what we do now is we remove the condition on the object text as well, right? So now we find people born anywhere. So this is a very simple pattern. But we can play around with this tool a bit more. So we could say, well, I'm going to comment back in Germany, and I'm going to comment out the verb. So what this gives me basically, again, is the same syntactic structure. So we have a passive subject, a participle verb, but it doesn't have to be born anymore. Now it can be anything in Germany. So now we have stuff like this is produced in Germany, this is headquartered in Germany, and so on and so forth. So this way we can actually explore the corpus a little bit. And I'd like to show a video of this tool in action actually at this point. Just so you see. Right. Okay, so this is the exact same thing that we just talked about. So I'm entering the sentence, Einstein was born in Germany here. And I mark the 2 entities, Einstein and Germany. And I also mark the relation phrases, the 2 words that evoke the relation, right? I generate this rule. So the sentence is parsed. You see the parse in the middle. The rule is generated, and the first thing that I do is I comment out the Einstein part, right? I fire this rule against the corpus, and in a short time I get back a bunch of hits, right? And now I can look through these hits and see the sentences in which this relation is found. So, for example, what you see in some of these sentences is that there are long-range dependencies in there as well. So it's not always was born in. There's stuff in between in some of these example sentences, right? So now I comment out Germany. Now we got a bunch of Dutch people, right? And the next thing that I do is I comment back in Germany. I comment out the born. And then we have more open information extraction style rules where we have all sorts of different predicates that follow the same deep syntactic structure, right? So that's what we get now. And we have headquartered in, developed in, married in. So all these different types of relationships, right? So I'd like to show a second example. This wasn't in the slides, but of a more open IE type of way of using this tool. So let's say instead of born in, we're actually looking for a more interesting relationship. We're looking for comparisons. So we want to know how do, I'll just skip ahead a little bit, how do 2 things compare in text? So if one thing is compared to another thing in text, how are these things compared, right? So we're looking for any comparison between 2 things. An example of this might be faster than. C is faster than Java. And we want to mine this kind of relation from text. So we have the same workflow. We invent a sentence and annotate it. But this time I'm even less creative than last time. I'm not even making up entity names here. I'm just saying x is larger than y, right? I say x is the subject. I have to put that in. X is the subject. Y is the object of the relationship. And the words that evoke the relationship are larger than, right? So I put that in. I generate the rule. And the first thing that I do is I comment out the text on the subject and the object. What this effectively gives me is an extractor that finds things that are larger than another thing as expressed in text. So East Falklands, for example, are larger than the West Falklands, at least according to the text. Now what I do, I'll just stop that. Now what I do, I also comment out the larger, because we're looking for any comparison, right? So I run this against the corpus, and now I get a whole bunch of different comparisons, how they are expressed in text. So I find stuff like younger than, smaller than, older than, and better than, and many other things. So I sort these by relation phrase. I look at the examples where this is from. And for example, I find out that the Joker is better than Scarecrow. Okay. Yeah, so basically this is the tool. And all you have to do is basically repeat this workflow a few times for all the patterns for the relation that you want. And you have your extractor, and you can run it on the corpus. So we evaluated it in a real use case. So I mentioned that I work in a European project with a bunch of libraries. And one of the use cases was from the Natural Library of the Netherlands. And basically what they want to know is which publisher publishes which content. So which journal is the domain of which publisher. And this is important for the libraries to know because they have to know who's responsible for what. But at the same time, it's challenging because there's actually a lot of movement in this field. So journals get discontinued, new journals appear, publishers merge. There's a lot of stuff that happens, and the libraries aren't always notified. So before this semi-automatic method, they basically had to do this manually by researching on the web, right? So this is really not feasible. So we use this tool to build an extractor for them. And this really is textbook information extraction, right? You have a customer that wants to have one specific type of information. We build an extractor, run it on the web, and give them the data, right? So we crawled a bunch of text from the web for this domain. I used PropMiner to define a small number of patterns, like X is published by Y, X is the publisher of Y, and so on and so forth. And we found thousands of instances, many of which were useful to our partner. We have a paper on that as well. And the great thing about it is that, at least for my part, it was only half an hour of work, right? I just used the tool. That was 5-6 patterns. That's half an hour of work. And the partners were quite happy. So this illustrates how such tooling can actually help. However, it also illustrated some of the drawbacks of this approach. And the first limitation basically is that, of course, one relation can be expressed in many different ways. And what we have to do is, first of all, we have to repeat this workflow for every pattern that we want. And what's even worse, I'm actually limited by my own creativity. So maybe I'm not coming up with all the right patterns, right? So I'm not creative enough. I come up with like 5 or 6, but maybe there's actually really good ones that I'm missing. And so for this reason, we started looking into more data-driven, data-guided approaches. So basically, what if I define a pattern that I like Y publishes X? I run this against the corpus, and the corpus, through statistics, returns to me correlating patterns, such as X is a publication of Y, and another one, Y's journal X. And the second pattern here, by the way, illustrates that patterns don't always have to include verbs, of course, right? So Y's journal X is basically mediated through a noun, but that doesn't matter because we are using subtrees anyway. So we're not limited to any verb kind of stuff. So yeah, so this notion of data guidance. So we've presented this work this year at Coling. And what we also did was we simplified the approach a little bit. Because in the end, if you're only looking for relations between two entities, then you can basically do away with the whole example sentence thing. You can just say fix the placeholders. X and Y are basically always the placeholders for entities, right? So instead of entering an example sentence, I just enter X publishes Y. That goes to a subtree. And we added this time entity type restrictions. So these are optional, but what we can now do is we could restrict the type of the X to be of type organization. So This is very useful because, for example, the pattern X publishes Y might be a person who publishes something, which is not what our partners want. They want to have organizations that publish journals, right? So basically, we added optional type restrictions in there as well. And the nice thing about this is that if we have this data-guided approach, is that we can now start the process with even more vague information. So we not necessarily really have to know where we're going. We basically work with the data gives us suggestions, and we basically navigate through this suggestion space. So the workflow now, the iterative workflow now, basically we start with an initial query. And this query has up to 3 fields. They don't have to, at least one of them has to be filled, but it doesn't really matter which one. So in this example, I'm saying so let's say this time we're interested in a person and their educational background, right? So my first query is, in this case, I actually limit the X type to be a person and the Y type to be of type educational institution. And I say, I don't really know about the pattern yet at this point. So I just want to see all the patterns that hold between these 2 types. This goes against the data, and there come back a bunch of suggestions, such as X is a professor at Y, X graduate from Y, X drop out of Y. And so I go through these suggestions, and one of them actually is interesting to me. So I'm actually interested in drop out for some reason. So basically what I do is I affirm this pattern, and I just don't want the other ones. This causes my query to be updated. So now my query consists of type restrictions, the same ones as before, but also the pattern X drop out of Y. And because now I have more information, I get better suggestions back. I get things like X attend Y but drop out, X leave Y, X briefly attend Y. Of these, I like 2. I don't like left because there may be different reasons for why a person might leave a university. And I'm interested in drop out. So I affirm these 2. These get, yes?
Maybe I missed something, but how are these patterns selected after you specified that you're interested in a particular dropout pattern? What happens?
Yes, so basically what we do is we calculate correlations between these patterns. So the selection that we have finds relation instances. And basically we look through these relation instances that the current selection finds, and we look at other patterns that match for this selection. And yeah, so these are the correlations. Right, so basically we repeat this workflow until we have a set of patterns for extractor. But we don't enter anything. We're basically just reacting to suggestions, right? We just say thumbs up, thumbs down, I like this, I don't like this. So this is very quick. At some point, there are no more good suggestions, and I mark the extractor as complete. I run the extractor on the corpus, and I find stuff like Bill Gates dropped out of Howard and Leo Tolstoy out of Kazan University, right? And I'd like to show a video of that as well. This tool, by the way, is online, so you can, the entire toolkit is online, so you can basically freely experiment with it. This is a screencast that we made, again, for our partners for digital preservation. So here, basically, we're trying to find out relations between software and file types. So digital preservation people are very concerned about file types and file types disappearing. And so we're trying to get evidence of how these file types are still used and this kind of thing. Since I'm not an expert, I basically just start with the types. I don't really know what kind of relations can hold here. And so I enter as an X type. Oh, yeah, maybe I should give some more explanations. So we have an X type and a Y type. The type restrictions that you see on the left and the right that I can select. And I can also select a pattern in the middle. Yes?
Where do you get an identity recognizer for all those types?
Yeah, so basically, there's a slide on that. But basically what we do is we do entity linking to Freebase. So the data set that we use is the ClueWeb corpus. So this tool is actually over 160 million sentences of the ClueWeb corpus, so it scales quite well. And the nice thing about using ClueWeb is that it's a very well-researched corpus, and Google actually released annotations for this data that link them to Freebase, entity mentions to Freebase. So we have very high-quality entity linking data, and we retrieve the entity types from Freebase. So we actually do have stuff like software, file type. We have a very fine-grained entity types, which is really nice. So.
What about new data?
Yes, new data, we can discuss that. So basically, we would not have this fine-grained entity types for new data, although there are some projects, FIGER, for example, from UW, right, which are entity taggers that even detect fine-grained entity types for unlinked data, right?
Plus, ClueWeb is like super big.
Yeah. I'm sorry?
How do you do the search?
Yes, so basically what we do is it okay if I do that after the demo? Because we have a slide on that, yeah? Okay, yeah. Okay. So, but just to see how quick it is, so this is 160 million sentences. So it's a sizable portion of the CRU web. Basically, it's all the sentences that have, all the English language sentences that have two entities in them. So this is why we selected these sentences, right? Yeah, so I can start with any of these fields. I could also start with pattern, just to make that clear, even though both examples are with types. So basically, I select, with autocompletes, I'm guided as well. So I select the types between which the relation holds, and I get a bunch of suggestions. And of these, by single-clicking on a pattern, I see a bunch of sentences where this pattern matches. And by double-clicking on it, I select this pattern for my extractor. And yeah, so I'm inspecting these patterns, and I like it. So basically, I select it, and now see how the pattern suggestions are updated. A number of things happen now. So I have my extraction results. So what we see here is the output of this extractor of the current selection. And basically, I can look through these results if they make any sense for me. So PaintShop Pro supports PNG format and this kind of thing. So I basically go through this list. And I also, in the middle, I see a bunch of suggestions for new patterns that might be interesting to me, right? Of these, I select, yes, open Y file in X, right? That's another pattern that correlates, and that's interesting to me. So I, again, inspect this pattern. And since I like this pattern, I select it as well. And now you will see that the suggestions are even better. So I'm getting a lot better relationships between tools that support certain file formats, right? And so, yes, this is also what I can do. I can look for patterns that contain certain words. And this search is also, this reflects basically my current selection, right, of the entity type restrictions. Yeah, and basically I just work with the data. I select a bunch of patterns until I'm happy. Let me skip ahead a little bit. Yes, and once I'm happy with the extractor, so I scroll through this, I can actually export this. And all of this that you see here, you can do on the web. So this entire thing is online. You can output your extraction results as well.
Can you get sort of aggregated results as you explore? To say that we're going to find 50 evidences for this particular XY?
Yes. So if you click on the, so they are aggregated. So they're grouped by entity pair, if that's what you mean.
Yeah.
For example, you might see Adobe supports PDF, and if you click on that relation instance, you see all the different sentences in which it was found, and all the different patterns with which it was found. So this is aggregated, yeah. Yeah. Right. So here's So here's basically how we pre-process the corpus. So what we do is we dependency parse all the sentences from the clue web. And then we use this data set provided by Google to link all the entity mentions to Freebase. And from Freebase, we retrieve the fine-grained named entity types. And what we also do, this is what we do is after we have the named entity mentions, we now generate preemptively all possible subtrees up to a certain size for this data. We just generate blindly all these subtrees and index them. We dump them into a huge table, which basically looks like this. Basically, each row consists of an X entity, a Y entity, a set of patterns that hold the type restrictions, and the sentence in which it was found. And so what we can do with this data set, with this data structure for now, is for example, we could ask, give me the most prominent patterns that hold between a person and an institution, right? We query for these two columns, and then we just group by patterns and count them, right? And then we have the most prominent patterns. And at the same time, we could say, give me all the entity pairs for which this pattern matches, right? We just look up this pattern in this table and get all the entity pairs in the sentences for this pattern. And so for implementation, what we did was we actually used Lucene to implement this. So we dumped all of this into a huge Lucene index. The index size is actually 400 gigabytes, so it's a pretty big index. But it is also a large corpus. It's 6 million distinct entities, 160 million sentences. And all of this is available through the web tool, and you will see that the response times are generally quite fast. We evaluated this. So the only way to evaluate this is sadly through a user study, because if the claim is this tool is very easy to use and you can arrive at your extractors very quickly, then you're going to have to sit some people down who don't actually have a background in relation extraction, right? We gave them a very short, 10 minutes, that's a very short introduction. We basically showed them how to use this tool, we showed them one or two workflows, and then set them to relation extraction tasks for relations, standard relations, born and died and educated at, graduate with degree. And we also gave them a more vague task. So we said, just find us any relations that involve celebrities and see what you can come up with. Yeah, so these are the results. Basically, I'll highlight one row. So this is more or less a typical result. So user 3 for graduate with degree, spending 8 minutes, selecting 24 patterns, finding 50,000 relation instances with generally high precision and low recall. And if we look at this, what we see is generally that the time is around 10 minutes per relation. We have tens of thousands of instances on average. We have a high precision and a low recall. And this is in line with other works in rule-based information extraction. Generally, if you have people write rules, the precision will tend to be very high because people are really handwriting these rules. At the same time, recall will tend to be low because they're not getting all the patterns.
So you said these users were not familiar with relation extraction?
No.
Okay. So were they like familiar with any NLP stuff at
No,
all?
no. So no relation extraction, absolutely no NLP. Some weren't even computer scientists. So yeah.
Did you combine all of the patterns of all of the users to get higher recall? That's my question.
Oh, that's actually a good idea. So we should do that. Yeah, we should do that. The exploration task. So here's my favorite one. This is which celebrity drives which car. So and Sarah Palin drives a Chevrolet, and I don't know. People drive different cars. So this is basically one that someone found, and people really like the exploration task actually. Right. So these are some patterns for the which celebrity drives which car relationship. So the user feedback. So basically one of the biggest problems is the halting problem. So when does the user actually stop adding patterns, right? They select maybe 20 or 30 patterns, and at this point they're already finding 50,000 relation instances. So, or users at this point basically just said, okay, it's enough, next relation, right? So when do you stop? And at the same time, how do you evaluate this, right? As soon as you're finding tens of thousands of instances, you can't really glance over the data and say, this works really well, or it doesn't work really well, right? All the users wanted more control over the entity types. They were generally not too happy with Freebase. On the one hand, the problem is that Freebase entity types the description is not so intuitive. There's stuff like location, there's weird stuff in there. At the same time, there are some limitations because you're limited to a fixed entity set, right? So they wanted to have basically the same process for building entity extractors and embedding this into the relation extractors.
They want celebrities, right?
Celebrities was there.
Oh, that wasn't it?
That's in Freebase, yes. Yes, yeah.
Is there a way to write patterns for higher order relations that basically combine two
Yes.
relations?
Not in this tool, but it's already online, but I'm not giving you the address because we're still working on that. So basically what we're doing right now is based on this feedback, users wanted to have entity extractors, wanted to be able to write their own entity extractors. And so basically, we are experimenting with ways of embedding extractors in other extractors, so basically higher order extractors. We're trying to expand this into a toolkit that you can use for knowledge-based creation and even for collaborative knowledge-based creation, right? So you might have a topic and you might have a few people and they work together on creating the entity extractors, the relation extractors for this specific knowledge base that they want. So this is work in progress. There's another thing, and that goes back to your question on different corpora. Basically, what we're looking at are two different corpora at the moment. So, of course, we want to do TAC KBP. We basically want to see how such an approach would stack up against these engineered approaches from TAC, which are mostly machine learning based, right? So, can we compare in any way to these systems? Another thing that we want to do, I think might be very interesting, is the medical domain, right? Right now it's very trendy to do information extraction on biomedical stuff. And what we want to do is basically load into this tool all this medical data, right? The PubMed abstracts and all that. Load it in there, put it online, and basically allow this exploration for all the people that want to do medical extraction. So let's see what kind of information they can actually find in this data, right? So basically, just make this available. So these are basically two things, two directions that we're thinking about right now. Yeah, so the summary for this part is we've made the case for exploratory relation extraction, presented 2 workflows and 2 tools for this type of exploratory relation extraction. And I would really invite you to try out the tool. It's online, it's linked on my webpage, and I'd be happy to get some feedback on that. Yes?
So it seems like there are 2 related scenarios that would require some further work. I'm curious what you think about them, further or different. So the one is, right, you said this is for people who aren't knowledgeable, but let's say we wanted to extend the usage to people who are more knowledgeable, or the users that work this become more knowledgeable. And related to that, right, you showed how it's easy to come up with relatively high precision but low recall, as is often the case. But let's say we wanted substantially higher recall and maybe even higher precision. So you kind of have to get, in both those cases, presumably, you have to get deeper into the process. And so I'm just curious, do you have ideas about how to extend this to go deeper?
Ideas, yes. So basically, one thing that you could do, if recall, for example, is really interesting for you. So one thing that we're thinking about is you design a set of extractors, right? For one extractor, you select a set of patterns. These patterns find for you maybe tens of thousands of relation instances, and then you use these for distant supervision, right? So basically, you could use this to generate distant supervision lists of tens of thousands of instances, and then use your machine learning approach on that. So if recall is really interesting for you. And this could be completely automated, right? Another idea, what was the second question? I'm sorry. The second question again?
I was also talking about more expert users.
Expert users, okay. So another thing that we have observed with users that liked the tool very much was that they requested additional complexity. So basically, making it very easy is good for getting people started. But people who use the tool a lot, they want to do more stuff. So in the end, what the idea is basically opt-in complexity, right? So once they're hooked, we can somehow give them more ability to work on maybe more like the previous tool, like the PropMinder tool, where you actually can look into the feature set and manipulate the stuff more fine-grained, on a more fine-grained level. So, yeah.
Now, with the distant supervision idea, you're going to get positive examples. How are you going to get negatives?
Probably the same way you always do. I don't know. So I mean, distant supervision basically always has this problem, right? That you have the positive examples, and then you need to do some sort of sampling for negative examples.
So you've reduced this to a previously unsolved problem.
Yeah. Yes?
The problem with, I think, most of the distant supervision approaches that I know for relation extraction is that they're also higher in precision, but have really, really low recall, maybe even lower than such tools.
Really? Okay.
I think actually what probably might work better is if you do some sort of clustering on phrases that you extract, or.
Well, in a way, this feedback is in a way the same thing that you would get through clustering, right? This feedback of giving related phrases that the user still has to select is basically distributionally similar patterns. So in a way, this was inspired by clustering. Okay. Okay, so how am I for time?
10 and 15 minutes max.
10? Okay, no, that's good. Because I mean, this is a side project, but I think it might be interesting to your work here, maybe. So basically, what we did here, we were interested in using open information extraction technologies to mine general world knowledge from text, Commonsense knowledge. Basically, common sense. I probably don't have to tell you this, but we're motivated by tasks such as this one, the choice of plausible alternatives. You probably know it. You basically always have a premise. You have a question: what was the cause of this? What is the result of this? And you have to select one of 2 options. 2 alternatives, right? So the premise here is the man broke his toe. The question is, what was the cause of this? And alternative A, he got a hole in his sock. Alternative B, he dropped a hammer on his foot. And the funny thing about these questions is that humans get these right in 100% of the time, and the machine actually doesn't, right? Another example, the police aimed their weapon at the fugitive. What happened as a result? The fugitive fell to the ground. The fugitive dropped his gun. Again, very easy. So the best published results achieve only 65% on this data set, which is not much better than guessing. And so we were motivated in modeling this kind of world knowledge, but actually what we want is a bit more than just selecting the right answer. Because the better thing would be actually, what if the program could actually explain its choice? So let's go back to this one. The police aimed their weapon at the fugitive. What happened as a result? The fugitive fell to the ground. And the program would tell us, well, I see the following sequence of events leading to alternative A. Sequence being the police aim their weapon, they shoot the fugitive, and the fugitive falls to the ground. And for alternative B, I see the following sequence of events. The police aim their weapon, the fugitive surrenders, and the fugitive drops his gun, right? And so it would be nice if the computer could actually explain the choice. That might even be more interesting, and then, of course, make the right selection. So what we need for this is common sense knowledge. So we need to know, especially we need to know what is possible in the world, and even more so, we need to know what is typical in the world. So what would we expect to happen, right? So what is possible, what is typical, and there have been some projects in trying to model such knowledge, for example, ConceptNet, which was a crowdsourcing approach, a hand-picked number of relations, part of, used for, so on and so forth, but it does have scalability problems. And also, I'm not really aware of ConceptNet being used for reasoning tasks. And so basically what we looked at is, what if we use open information extraction on just incredible amounts of data, and not just OpenIE, but also distributional semantics, just basically throw everything that we have at data and see if the problem goes away. And for this, we created the Weltmodell, which is our knowledge base. So basically, open information extraction, we go through a bunch of sentences, such as when the waiter had brought coffee, when a waiter had brought coffee. We use OpenIE, but only on non-proper nouns. So basically, if we see a sentence like this, what we learn is that it is possible that a waiter may bring coffee. If we see this once, then it's possible. If we see this many, many different times, we might even say that this is typical, right? And we're very much motivated by a data set that, again, was released by Google, a data set of dependency tree fragments compiled over 3.5 million English language books. So this is a huge data set, 10 billion distinct dependency tree fragments that we can mine, which means we have incredible redundancy in the data. And using open information extraction on this data for non-proper noun, we get millions of distinct facts. And what this fact basically tells us, so what we do with this is basically we generate a matrix of concepts and statements. So a concept, that's basically all the roles, those are the nouns. And the statements are the statements that we have observed for this concept. So if we look at one of the rows for coffee, right, then we see that someone may drink coffee. Some may sip, coffee may be served, that's a unary fact, so we're doing n-ary open information extraction. And somewhere down there we also see waiter may bring coffee. So basically these are the placeholders where coffee goes in, right? And we also have counts. So for example, someone may drink coffee, we observe that over 10,000 times in the corpus. So this basically is an indication, yes?
So all these are a single concept, or is each one a separate concept?
So basically we have a concept, which is a noun. So the matrix has the concepts, and the statements are the columns. And the statements always pertain to one concept, right? That can fill the placeholder. Yes?
Do you have named entity on top of this, or is someone just any entity?
There are no entities because we're only using non-proper nouns. Well, someone basically is we have some manual normalization. So if it's he or she, we normalize that to someone. But aside from that, we just use the nouns as they appear in the text.
Okay.
Yeah.
In this case, it's all based on pronouns?
Yes, yes. So someone is, yeah, we normalized a few things. So there's a lot of handwritten stuff in there. But for the most part, it's very general. We just take it how it's used in the text.
And you just ignore things like Bob drinks coffee, that would just be ignored?
Yeah, thrown away. Because we don't know if the entity is like a person or an organization. So as soon as it's a proper noun, we really don't know what's happening. Right? But we don't only have the occurrence count. So I mentioned that we've someone may drink coffee, we see that 10,000 times. What we can also do is with this data, we can use compute measures of association, right? Point-wise mutual information, normalized point-wise mutual information, lexicograph mutual information. And basically what we interpret these as are typicality. So for example, if we have the concept coffee and we don't know what else is happening, we might know that someone could drink it, it may be served, and so on. And if we look at it from the other side, it may become more clear. So if we look at all the things that a waiter may bring, right? So let's look at a column now. All the things that a waiter may bring. And so the top things might be a check, a drink, coffee, bill, food, breakfast, and so on and so forth. Again, we have the counts, we have the mutual information values, and in a way this tells us the typicality of this. So if we know the waiter is bringing something and we know nothing else, these kind of statistics could help us infer that he's probably bringing either a check or some food or drink, right? This is basically just a modeling something, possibility and typicality. And now that we have this matrix, we can actually go further, right? So we could compute the similarity of concepts, obviously. So we can compute the similarity of concepts by doing the cosine distance over their statement vectors, right? And if we do that, we find out that coffee is functionally similar to tea and other beverages, right? And the nice thing about this, again, is that we don't only have a number, but we can actually see how they are similar. So we can ask, why are coffee and tea similar? Well, because you can drink them, because they may be served, and so on and so forth, right? The same thing we can do for everything. So basically, we do the parallelized similarity of all these concepts. And now that we have that, we can go back to the waiter bringing something. Because what we now can do is cluster all the concepts that the waiter may bring. We have the pairwise similarities. We know check and bill are similar. We know waiter can bring all these things. So we execute a clustering on this data, and we find groups of things that the waiter can bring. So again, we're going back to the situation. We have a waiter coming. He's bringing something. We don't know what. But we can now tell it's going to be something of these groups. It's either going to be like something like a check, bill, piece of paper. It might be, this is a big group, drink, coffee, food, blah, blah, blah. And there's a third group here. It might even bring tray, plate, dish. So that's another group of things that the waiter may bring. So again, this is world knowledge and possibly useful. We can go a bit further still. We can now do the distributional similarity of statements as well, right? So for example, what do we know about things that the waiter may bring? So we now do the cosine similarity for the statements. And what this tells us is that things that the waiter may bring may be on the table, may be served, may be put on the table. Because all these things that fill this placeholder basically are similar to what the waiter may bring, right? So we have the cosine similarity on this level. And this gives us, again, perhaps some information that we might find useful. Yeah, so this data is available, and this is also browsable. It's linked on my website. There's a nice GUI where you can look through all this data. You can even execute the clustering and basically see if this data might be useful. So we're making this available and see if this data might be useful for us to model some sort of world knowledge, common sense thing. We are looking at a few things at the moment. So the list is quite long, but I think one of the main things that we're looking at is inference at the moment, especially through matrix factorization. So the preliminary results are looking pretty good. So basically what we're doing is inference through matrix factorization as a matrix completion problem, right? Because even if we have all this data, there will still be true facts that will not be explicitly expressed in text. Yes?
What do you mean by inference?
Basically, we're doing missing value, so matrix completion, missing value imputation. All right.
You talked about Corpora at the beginning, so are you using this for Corpora?
It was motivated by Corpora. We tried to throw it at Corpora, but the results were not so good.
I don't even see it. How would you throw it at Corpora?
Yeah, so we were hoping that this whole explain thing, so maybe the fugitive, so what is typical, right? So the police aiming their gun, and if the gun is aimed, it's often fired. Like this kind of thing, relationship to...
So you need to relate two statements,
yeah.
just the database of individual statements.
That's the problem. That was basically the main problem at this point, is that we don't really have causality between these different statements. But we would be happy to add that in some way. So if we could mine that, that would be really good. So it was motivated by Corpora, but we are not yet so far as using it for Corpora. Yes?
So you had said that you're working on higher order, being able to write patterns for higher order relations. Is that still within a single sentence? It's not intersentential?
It's still within a single sentence, yes. Yeah, I'm almost done. I think my time is already up. But just to wrap this up. So another thing is Turney's analogy questions, which might be an interesting application of this. But yeah, so please try it out. So I'll conclude. First, we made a case for exploratory information extraction, which is user-driven and data-guided, trying to make it very interactive, very easy to use, and very quick, that we arrive at our extractors very quickly, and make it suitable for novice users. And the second part is our Commonsense Knowledge base, where we basically looked at what can we mine out of text. If we have a lot of text, if we have cool technologies, what kind of Commonsense knowledge can we mine from text? And could we possibly apply this at one point for some tasks? And this data is available. So yeah, thank you.